Okay, so we're going to talk about the concepts behind the normal distribution. The two things that differ from normal distribution um, to different normal distributions are going to be your mean and your standard deviation. So basically, this is your center and this is your spread. That's the only differences between any of the normal distributions. Each one of these three is different in that they have different means and different standard deviations. You can see that some are tall and skinny, some are wide and short, some are kind of in the middle. And it just depends on those two numbers. Otherwise, they are set up exactly the same to encompass the right amount of area depending on those two factors. So you can see here that this one in the middle is very tall and very skinny. Well, it has a mean of 40 and a very, very small standard deviation compared to its mean. So when we look on the scale, to the left and right of the center, it's very, very little difference. And that's why it's so tall, because the standard deviation is quite small. For our first one over here, we have our mean at 10 and a little bit larger standard deviation, so it moves out further than our second one does. It's pretty tiny difference, but you can see that all the mean does is shift it left or right along this axis. So it doesn't really affect the size as it does kind of where it is. And that's going to come into play a lot later on. And then finally we have our last one, which our mean is at 70, and we have a very wide standard deviation of 10, much bigger than than the other two. So it still encompasses the same amount of area, one standard deviation above and below, but it's just a larger standard deviation. So it's got a flatter curve. But the only two things that matter are your mean and standard deviation. Everything else is consistent from each different type of normal distribution that you can run into. So this is very much what it's going to look like. Your mean always is going to be right in the middle. So there's a symmetry left and right. So this is your mean, directly in the middle. 50% of your data will occur before, and 50% of your data will occur after. So that's where we find our probabilities. From the mean, whatever that is, one standard deviation left and one standard deviation up encompasses the same amount of area because it's completely symmetric. If you go to the left and right the same amount, you're going to have the same probability of either direction, and so on and so forth. Now, the way you draw the normal distribution is it curves up, and then it starts to kind of curve back down, and then it kind of curves back around again. So it's this nice like bell or kind of hill shape. But again, the only thing that matters is where your mean is and what your standard deviation, how far left and right we need to move to encompass certain types of area. Now, when we're trying to figure out certain probabilities, we have to look at these in different ways. For this distribution, we're looking at the probability that our random variable is a greater than 8. So if it's greater than 8, and you can see this on the graph, we're looking at 8 or more, all the way to the end. Now this is this huge shaded area all the way to the end. So this can technically include numbers all the way up to 1 billion, even though the probability of that's going to be very, very small. But we still want to account for that. It could be any possibility that's greater than 8. Now, the second one asks us to go between 6.5 and 8. Well, we're looking again at an area. So 6.5 and 8, we look at this area underneath this curve. And that's what's going to tell us the probability that our random variable is between those. Now, what we use for the normal distribution is this function that you'll find on your calculator. It's a normal CDF. And the normal CDF behaves in this way. You have your lower bound, you have your upper bound. So those are two different ones, and I'll show you in a second what those are. And then you type in your mean and your standard deviation. So if you have a different calculator, it may just do these in order from top to bottom if you have your own window, but that's the information that you can put into any normal CDF, which is, this is going to tell you the probability that your observations occur between these two limits, so your lower and upper bound, given what your mean and standard deviation are for those particular for that particular distribution. Now for the blue one, for A, if we were going to do greater than 8 based on our mean being 8, or based on it being greater than 8, you would do this. You would say your normal CDF, your lower bound is going to be the bottom, so that's 8. Your upper bound, we don't know what that is, and what we do on the calculator in order to make sure that we don't make any mistakes is we type in basically infinity, but with your calculator you're going to type in 1e99. That is kind of, it's 1 times 10 to the 99th power, which is such a huge number that it's going to make sure that you get as accurate an answer as possible. And then you type in whatever your mean and standard deviation are for that particular distribution, which we do not see here. And for our next one, so kind of our, I guess it's kind of peach or purple or salmon, whatever, you would say your normal CDF, your lower bound is 6.5, your upper bound is 8, and whatever your mean and standard deviation happen to be for these, that is what you would type in, and that would give you your answers for those particular problems. So your mean and standard deviation are key, and you just need to figure out what your lower and upper bounds are given what type of problem it is. And so, for example, just to cover this, this one goes all the way up to infinity. If you were going the opposite direction, down, then your lower bound would be negative 1e to the 99, so that would be going first. But so just keep that in mind. Now, there is one type of distribution that we use quite often when we don't, when we're using z-scores as lower and upper bounds, or in other times if we're using something what's called a standard normal distribution. All this is a very special one where your mean is 0 and your standard deviation is 1. Note, it's not very complicated. Because this is all based off z-scores. So you have your mean, which is 0. Your mean is a z-score of 0 because you are 0 standard deviations away from the mean. Well, if we went up 1 standard deviation, this would be your mean plus a standard deviation. That is a z-score of 1. So your z here, so z equals 1. Now, if you went down 1, you would have your mean minus a standard deviation, and that is a z-score of -1, because you are 1 standard deviation below the mean. Now, using the standard normal distribution, we could find lots of information about different problems, and we'll use this quite often. Like if we were to try to find, like, what is this area in between these, going back to the previous slide, we need to use our normal CDF. Now, our lower bound is going to be, now we're talking about z-scores. So our lower bound is going to be -1, and our upper bound is going to be 1. Well, all we need to do is just define that we are using a mean of 0 and a standard deviation of 1. Now, your calculator will automatically use 0 and 1 unless you tell it otherwise. But if you want to get in the good habit of just making sure you write the mean and standard deviation, you would write 0 and 1. And this would give you somewhere around 68%, which, when we talked about the empirical rule earlier, that's the number that we use for 1 standard deviation below and above the mean. But you'll get an exact answer or more of an accurate answer, excuse me, if you use your normal CDF function on the calculator. So again, this is kind of what your standard normal is going to look like. You've got your mean at 0. You've got your different standard deviations here. So this is where this comes in. Now, there is a different function that we are going to use to find particular z values. This is called INV norm, or inverse norm. Now, inverse norm, what that does is it's going to ask you to plug in your area, or what you'd consider your probability. So, the probability. And then you can type in your mean and standard deviation after that, and it will tell you where the cutoff is for the area below that number. So we're going to look at examples in the example problems, but what inverse norm does is it counts all the way up to a certain point where below that number, this percentage, whatever that probability is, this percentage exists below that number based off of whatever mean and standard deviation that you do have. Now, one rule when we're using the normal distribution is that the whole area that you have adds up to 1. So we can use that to our advantage when solving problems. Like if we were to know if we knew that our area above a certain point was a certain number, then we can use that. We can say, okay, well, we can find its converse by subtracting that amount away from 1. So any two sections add up to make 1. So I could have section 1, I could have section 2, and both of these add up to make 1, which is very, very helpful for us. So you can just use regular algebra to figure out the rest of this. It's extremely helpful mainly when you're trying to find area above a certain point, because we can find the area below a certain point and subtract it away from 1 to find what we're looking for. Now, what happens if we're trying to find the area between 2 points? Well, what we do is we look at the area up to a certain point. So we go to here, okay? So we find this area. Now, if we were looking for, let's say, this particular portion here, all we have to be able to do is take away what is below this section, okay? So we cut off, we subtract away this point. So we start here, that gives us this whole area all the way down, but we cut off everything below this point, so like that. And that will give us that area. So when we're looking for area between certain points, sometimes we start at the top, count everything down, and then we take away everything below a certain point, so that gives us only what we're looking for. And now, if you ever need to figure out an actual value again, if you know what your mean is, and you know what your standard deviation is, and you know the z-score of that said thing, what we can do is you take your mean, and you're going to add whatever that z-score is times the standard deviation. You're going to multiply that. And so, you know, if I had, for example, a z-score of, if my z-score was 2, okay, and my mean was 5, and my standard deviation was 1, okay, then what this means is that my distribution starts at 5, and each time I move up 1, Well, if my z-score is 2, that means that I'm 2 standard deviations above the mean. So I'll be looking at 7 here. That would be how I would get back to an x value or whatever I'm looking for, given that I know the mean and standard deviation.